This video presents the paper Unsupervised Discovery of Object-Centric Neural Fields. Given a real image with visually rich objects, our method can infer factorized 3D object-centric scene representations, enabling reconstruction and manipulation from arbitrary novel views. Building factorized 3D object-centric representations from a single image is fundamental to human vision and is a long-standing topic in computer vision and machine learning. Similarly, unsupervised 3D object discovery aims to learn object-centric representations from unannotated image collections. However, previous methods fail to generalize to complex real-world scenes. For example, in this kitchen scene with specular objects, existing methods may fail to identify any foreground objects, resulting in extremely poor scene reconstruction results. The major challenge faced by previous methods lies in their object representation. They represent each object in the viewer's frame, entangling intrinsic attributes such as shape and appearance with extrinsic viewer-related properties, such as the object's location. In this example, two identical chairs appear at different locations in the two images, yielding different object representations and reconstruction results. In contrast to existing methods, our model disentangles object intrinsic properties with object location, which is explicitly estimated and represented by a 3D coordinate. This design leads to invariant object representations and substantially better generalization. Our model has three submodules. The encoder first extracts a spatial feature map. The latent extraction module infers the object's latent representations and positions in the underlying 3D scene from the obtained feature map. After obtaining the object latents and positions, we use the object nerf decoder to recover the background and individual objects, then compose them to reconstruct the scene. This pipeline enables us to put the objects into the object-centric frame, facilitating learning object priors from synthetic data that are generalizable to limited real data. The object-centric learning pipeline involves three stages. In the first stage, the model is trained on single object scenes. We collect one synthetic dataset and two real-world datasets to evaluate our method. The synthetic room dataset includes chairs with diverse shapes and textures. The real-world kitchen datasets feature varied kitchen backgrounds and objects from multiple categories. These are the scene segmentation results on the room dataset. Our method consistently produces high-quality scene segmentation results, demonstrating its effectiveness in learning object-centric representations. These are the rendering results of individual slots. The baseline method puts multiple objects in the same slot, while our method manages to distinguish the objects. These are the results for scene reconstruction and novel view synthesis. Contrary to prior methods that all fail to reconstruct the scene, our approach reconstructs the scene with high fidelity and can even approximate the lighting and shading. These are some additional results for scene reconstruction and novel view synthesis. As shown, our method can even handle scenes where objects occlude each other. Finally, we demonstrate our method's ability in scene manipulation. Due to the disentanglement of object intrinsics and location, our method readily supports the following scene manipulation functions. First, object removal, where we remove certain objects when compositing the scene, and second, object translation, where we modify the object's position sent to the decoder. Given these input images, our method identifies the objects in the underlying 3D scene, reconstructs it, and manipulates the objects in it. To conclude, in this work we propose a novel framework for 3D object discovery based on the object-centricity concept. To evaluate our approach, we collect 3 challenging real-world datasets. Finally, we demonstrate that the object-centric design, combined with proper training strategies, can significantly enhance the generalization ability of unsupervised representation learning.